Good morning, everyone. Thanks for attending this presentation. I think it's an off-topic regarding the whole topics that we have seen. It's not related to construction management, unfortunately, but it's related to machine learning, so that's why it's participating in this conference. Before I present this presentation, the highlights of the presentation, as seen from the title, it's machine learning and blast resilience. Blast is the explosion, and resilience, I'm going to talk about it later. So this presentation, we will talk through an introduction and background for this topic, and then the methodology that we used, moving forward to testing some of the models that we have developed, and then we developed something called PI diagrams that we are going to talk about it later. So first, I would like to talk why we specifically picked blast loading. As you can see from here, blast loading that can come from explosions or even can come from accidental events. For the intentional events, which is mainly terrorist attacks, you can find that explosions are having the largest portions of terrorist attacks during the time worldwide, or even, as Professor Isaac said, it's very important in the Middle East. So that's why it's one of the important topics that we are studying. That's why we're talking about blast. And during this presentation, we are going to apply the methodology that we're going to talk about on reinforced masonry walls. So before I start, I'd like to introduce what's meant by reinforced masonry walls. They are concrete blocks with a void inside, with the reinforcement. It acts as a regular concrete wall, but composed of blocks made of concrete, and then we put in the blocks some grout to act as an integral walls. That's why its performance is almost like the reinforced shear walls, and it's applied, or it's commonly used specifically in Canada and the US in administrative buildings, where they use it as the facades. That's why it's an important, where it's the first element subjected to blast loads. And moving forward to resilience. So as you can see, as you have listened at the beginning, this session is about resilience. Resilience can be defined in different aspects. Every presenter will define it from his perspective, but by the end we will find some sort of key points, which is the capacity or robustness, where it's the capacity of a building or of structure or of a system to overcome an incident, and then the ability to recover back after a specific time. And to quantify this resilience, we have to quantify both of them, which is the capacity and the recovery period. In an engineering perspective, we present it in some sort of called resilience triangle, where resilience triangle based on having a functionality and a functionality loss after a hazard, where the rest of the functionality loss can be called as robustness, and then any system would have to be repaired or have to work again after the incident will take some time, which is defined by rapidity or downtime. And during this presentation, we're going to talk about a key element that we can use to define both of them for reinforced masonry walls, which is one of the most important elements in administrative building that can be subjected to blast loads. So just as an introduction for blast design, during in the current North American standards, which is the American and the Canadian standards, which is almost similar to other standards, to define or to design against blast load, you have to define a threat, which is basically the threat that's going to happen in front of the building, which is the charge weight and distance standing out of a building. And using this, you start to classify the elements, to classify the performance of each element that's subjected to this blast load, and finally to integrate this into a level of performance where you can classify the whole performance of a building, either it's high performance subjected to blast load or low performance, whatever, depending on the components. So what's this related to the resilience? As I mentioned, resilience is about measuring the robustness and the recovery or the downtime. So one of the key elements of blast performance or of dynamic analysis is having something called pressure impulse diagram, where any element can be defined, any structural element can be defined using the pressure and impulse, where pressure is the maximum load or classic maximum static load that can be subjected in front of the wall or in front of any structural element, and impulse is the integration of this, or mainly the energy of this explosion. So if we define the pressure impulse diagram for any structure or for any components, we can define the performance of this component. If we integrate this into current, or there is an already developed resilience framework where you can use the pressure impulse diagram using different functionality indices, where you can define the building as either functioning or not functioning, due to having sort of superficial damage when it's happening blast load, or more than superficial damage, where superficial damage you're not expecting a repair or a stop in the functionality loss. However, rather than the superficial damage, you're expecting a complete stop of the functionality of the building, and then you have to repair it. That's how it works in the resilience triangle. So our main target is to develop the PI diagrams. So why we are using machine learning? Specifically, in the current blast modeling techniques, there's two aspects you have to look into it. The first one is the blast load, and the other one is the structural modeling. The blast load, there is several criteria you can define it. Either you can simplify it, or you can use it accurately. You can use it accurately using CFD method, moving to parabolic simulations or triangular simulation, which is the simplest one. And regarding the structural simulation, or to model the walls or to model any structural component, you can also model it using micro modeling with a complicated modeling, moving forward to macro modeling, which is the easiest one. However, even if you modeled the triangular and the macro model, which is the two simplest ones, first of all, you are losing accuracy, and the second, it's still time consuming. As I mentioned, pressure impulse diagram, it's a generic curve that's used or can be developed using multiple points. So you have to develop one curve, you have at least to develop several points to develop this curve. So using simplified approaches, using the currently used finite element approach, it's timely consuming. That's why we started to look into different methods, which is incorporating machine learning. So in our developed model, we split the input models or the input data into 5 aspects, mainly with 2 categories, the load and the resistance functions. The load, or the pressure and impulse diagram, which are the 2 main components that's defining the blast load. As I mentioned, the pressure, as you can see at the red at the top, the pressure is the maximum pressure that happens due to the blast load, and the impulse is the integration of this pressure over time. And as for the resistance function, we used the simplified resistance function of generic walls, which are the stiffness, which is K, the maximum capacity, which is RU, and the vertical reinforcement ratio, S. We already found this as one of the influencing components in the structural performance of such walls. Ultimately, or the output goal of this model is to calculate the theta. The theta is the chord rotation of the wall. So when a blast happens, we're expecting the wall to get a curvature, and this curvature is the damage state that defines the performance of a wall. So our goal is to use these 5 inputs to get our theta, which is our output that can define the performance of a wall. And using the theta, we can develop later on the pressure impulse diagram. So we used an experimental published database from the ConWeb database, which had 100 experimental data covering a sort of aspect. It's well known that 100 point, it's not a huge data set. However, within the interval of this data set, it can give us an idea about the data that we are developing. So our methodology that we used several techniques. We used multivariate linear regression and polynomial regression. We used random forest regressions, and finally we used artificial neural networks. For the multivariate and polynomial, we developed sensitivity analysis for the polynomial. We found that the second degree was most efficient, as it gave us almost R score similar to the other ones. And as for the random forest degrees, and as for the random forest regression, I'm sorry, we found that 103 would give us the best one. As for the artificial neural networks, we developed 30 architecture for the neural networks, and we picked the best one, which gave us root mean square error for the artificial neural network with 0.35, which we used later on, where we used this model, where we used the artificial neural network to develop a PI diagram where, after simulating the blast load, we used it in a sort of a Monte Carlo simulation where we developed, or we input different P and I diagrams for any specific wall, and using Monte Carlo simulation we can develop or we can calculate the theta or the chord rotation of the wall, and from these calculations we can get the whole curve of the PI diagrams. As a sort of timing or time consuming, the PI diagram for like one curve of PI diagram would consume 6 minutes, around 6 minutes. However, when we used conventional finite element modeling, it can take us several hours, depending on the accuracy and the type of a model that we are using. So that's one of the interesting things that we discovered using the machine learning for this database. As a conclusion, we concluded that we tried 4 different machine learning techniques, where we found that the second degree almost showed the most reliable techniques from the regressions, and using 100 random forest or 100 tree gave us the best estimate using the random forest techniques. And also the linear regression was the least accuracy. And the artificial neural network showed us deviation about 20%, and we were successfully using the methodology that we used for developing PI diagrams that it can be used or can be integrated into the ongoing resilience framework that's already published. And I'd like to acknowledge my university, and thank you, and waiting for your questions.